All right, so with the power property, you drop the 7 down to the front, and then it's 7 times that log. That's going to help us a lot when we go to solve equations in the next section. That can be a pretty handy one to have. But that's as far as that one expands, because there's nothing left in here with the x. On this one, what's going on between the 3 and the x? They're multiplying. So to expand that one, multiplication turns into what? Addition. So log base 2 of 3 plus log base 2 of x. It splits the log into 2 separate logs, one, with each factor or part that's multiplied together. Okay. All right, so we've seen the power property. Here's the product property. Next is the quotient property. And we're looking at that one and saying, okay, there's division in there. So division with exponents turns into subtraction. So this is log. That's really log base what? 10. Remember that. That's important. But that's log base 10 of x squared minus log base 10 of y. Now, it's always whatever's on the top minus whatever's on the bottom. It makes sense that that's how it would be, because that's how you do exponent rules. Okay. Now, could either of those be expanded a little bit further? Using either the power rule or the product rule, product property. Well, I see an exponent on this x squared. So the power rule says, oh, that 2 can come down to the front. So that would end up being 2 log of x minus log y. And that would be the expanded form of that one. Okay. You're not done until it won't break apart in any other way. Okay, not done until it won't break apart at all. Look at this one. What's the big thing that's going on in this one that makes it look tough? The division, the fraction stuff. So what's that turn into? Subtraction. Log base 6 of 5x cubed minus log base 6 of y. Which one of those will split apart and simplify or expand a little further? The first one, yeah, it's got 5 times x cubed. So the 5 times x, that's going to give us a log base 6 of 5 plus what? Log base 6 of x to the third, but the third power can do what? Drop down to the front. So we could put that 3 in the front right there. And then the other one doesn't change. So we've expanded this logarithmic statement into several logs. That's not incredibly terrible there with that. You just got to remember, keep going until nothing else can happen. All right. Let's look at this one. Log base 2 of 4x over y to the 5th. So we could have log base 2 of 4x minus log base 2 of y to the 5th. That's taking it one step at a time. You're welcome to do more than one step at a time if you want to. What could the next line read? Well, log base 2 of 4 plus minus what? Good job. And that's expanded as far as it'll go. After you've done several of these, some of you probably can do it now, do that in one step. And I'm fine with that. Being able to expand it or condense it in one step. We're going to condense in just a minute. The expanding really helps us learn the properties. The condensing is what really is going to help us in solving equations later on. Okay. So let's do this one. Let's do natural log of 10x to the third cubed root of y. So they make it a weird one. Let's make that x to the fourth so we don't get confused with the threes. That'll make it a little more simple. But when we say 3, we're talking about the cube root, not the other. So what's going on between everything inside of that log? Multiplying. So the expansion of that would be addition. So everything's going to split apart into addition. So that's natural log of 10 plus natural log of x to the fourth plus natural log of the cube root of y. What's that equal? What else can happen? Okay, 4 drops in front, Alexis. Okay. Yeah. Yeah, I mean, it's part of the problem. So it's natural log, not log of 10. If it was log base 10 of 10, then that would turn into a 1. Because log base 10 of 10 is 1. You could simplify a little bit there. But since it's natural log, it's not going to go away. That's an ugly decimal number. That ends up in. So Trevor said the 4 could come down to the front. What about the cube root of y? Yeah. That is really y to the 1/3 power. So that would allow you to pull the 1/3 out to the front. And get that. The cube root is really the 1/3 power. We remember that from chapter 6, which allows you to pull the 1/3 out in front, drop it down with the power rule. And you've expanded it completely. Again, the expansion is really to help you learn the properties. The condensing is what we're really going to use the most, and when you go to solve equations in a little while. Okay, all right. Let's do some condensing. See if we can get there. So I call it condensing. Or write as a single log. So I think the write as a single logarithm may be how your book says it, but I call it condensing because you're taking something that's expanded out and trying to make it into something smaller. So you're condensing that. All right. So the original problems are going to look a little, they're going to look like the answers we got up here. The original problems are going to start out in that kind of style. So let's say we start out with this one, log base 2 of x plus log base 2 of y plus 5 log base 2 of w. They all have the same log base. That's kind of important, but it's going to be one of those things where they're not going to mix them together on you. I mean, they're all going to be the same. But it is important to note, like when you go through higher level math, they might mix it together then. So the logs have to be the same to be put together. That's what makes them like terms. Okay, so what's going on between everything here? It's addition. So addition, when we go to think about our log properties, addition came from what? multiplying. So what's going to get multiplied together here? Log base 2 of x times y. And what about this last piece? It'd be w to the 5th. Whatever's here, that goes up. So w to the 5th. It really doesn't matter what order you put those in because it's all addition. I put it in alphabetical order just because my OCD kind of just says you got to. But mathematically, you don't have to. Y or w to the 5th times x times y. That's condensed all the way, and that would definitely be handy when we go to solve later on. Okay. All right. Let's look at another one. Maybe mix some of the other properties in there with it. Log base 7 of 3 plus 2 log base 7 of x minus log base 7 of 5 minus 3 log base 7 of y. A lot of stuff in there. But it's expanded all the way. And what we're trying to do is get it down to one thing. Okay? So the ones you're going to get they're going to be expanded out, and you should end up with one single logarithm at the very end. Okay? So what do we see in this problem that wasn't in the previous problem? There's some subtraction in there, so that means there's got to be some what? Division. That's right. So what's getting multiplied together and what's getting divided by? Well, I see a plus sign between these two guys, right? So they must be multiplying together. So it'd be 3 times what? X squared. So when I try to condense that, I'm going to have log base 7 of 3 times x squared. Both of these are subtracted. So that means both of them are going to go where? In the bottom, the denominator of the fraction that we create here. Both of these have positive signs. Think about where does a negative exponent end up? In the bottom most of the time, right? That's how you fix it, is you move it to the bottom. So those are both negative, so that they're negative, so they go to the bottom because they're what you're dividing by. So what's on the denominator here? 5y to the 3rd. And it's condensed. You're done. So we've taken this big long thing and written it as one logarithm so that we can have less to write, less to remember, maybe. Let's do another one. Let's say we had natural log of 4 plus 5 natural log of x minus parentheses natural log of y plus 4 natural log of w. So throw some parentheses in there. So it could be done in one step, but it doesn't have to be. I think so. One of the easiest things to do.
So why didn't you do that like on H?
Because the original problem wasn't written that way. So like the original problem is written this way with the parentheses. That one wasn't. So what you're saying is this one could be written like H?
Well, I was just wondering, so I know you said like minus 3 log 7 5, it still goes under, but I was thinking log 7 5 minus 3 would be like another division instead of multiply. It's just subtracting, not adding.
But
So then I was like, why is it?
You're overthinking a little bit. We're trying to get one problem out of it. So we're not dividing the 5 by the y to the 3rd. We're dividing the whole, whatever is inside of the log by that. That minus sign on it means, okay, this is the division part of the log, the single log that we're trying to get there. So with this one, Could you condense each parenthesis separately? I think maybe that's the easiest way to go about thinking about this one. And then maybe once we see the end result, we can do it in one step pretty easily after that. So what does the first parenthesis on the left turn into? 4x to the what? Fifth, yeah. Natural log 4x to the fifth. Minus, and then this one turns into natural log of what? Y times w to the fourth. I'm going to write it w to the fourth times y because I just can't stand to not do that. And then how does this condense? Division, because it's a minus sign in between them, right? So we could have natural log, what goes on top? Yeah, 4x to the fifth. On the bottom, w to the fourth, y. You've gotten that there. Kind of to kind of revisit what Caroline was asking about, or commenting there, she's right that this is kind of the same thing. This one, if it were written like this, log base 7 of 5 plus 3 log base 7 of y, with the minus sign all out in front, it's the same thing as this. So whichever way you want to think about it, it works the same way. It's kind of like one of those things where, we got frustrated in chapter 6 a little bit because the exponent rules, no matter which order you did them in, it always ended up, you could end up with the same answer, even though I didn't do it the same way they did. And that's okay. These are logs, they're exponent rules. So you can kind of do it a different way and still end up with the right answer, even though somebody else did it in a different order. As long as your operations are legal, you can do that. Okay. Let's try one more of these, and then we'll look at solving some equations and actually putting this into action. I think that's where it actually starts making sense, is when you start using it some. So let's use log of 8 plus 2/3 log y minus 6 log x plus 3 log z. Trying to throw it as tough as it gets here, I think, for algebra 2 to play. So we got log 8, 2/3 log y minus 6 log x plus 3 log z. So what operations are we seeing in this problem? In addition and subtraction, which turn into the multiplying and division. So what gets multiplied together? All the additions, right? How many addition pieces are there? There's 2 in the front, but there's 1 in the back as well, right? So there's 3 pieces that get multiplied together because there's 3 plus signs. Okay, so what does the multiplication turn into? 8 y to the 2/3 z cubed. And then the division is just the minus one. What are we dividing by? X to the 6th. It could be written in a different way. You could write it log of 8 z to the 3rd cubed root of y squared over x to the 6th. Understand that these two are the same way. I would take it either way on the quiz. I don't care which way you write it. Just understand that if it, on the test it happens to be multiple choice or something, it could be written either way. They're both correct. That the 2/3 power is the cubed root with a squared inside. That makes it goes back to that chapter 6 material that we talked about back before the end of the course. Okay. All right. So there's 7.5. Let's go ahead and do some 7.6 and actually put some of this into practice. So this is going to use some of the things we did yesterday and what we're doing today to do it, depending on the problem, whether or not you need to use log rules or not to solve it. Some of it's going to be exponential, some of it's going to be logarithmic. So we're going to solve some equations today, and this will be the last bit of teaching you'll hear me do, like directly in front of you for the year. Some of you for your life. If it makes you sad, it's okay to cry. All right. You guys tend to always like solving equations better because you get an answer, you get x equals something, so it makes some sense. I always liked equations better because I got an answer. I felt like I completed something. So let's look at some equations, and we're going to just, through experience, figure out what's the best course of action to solve some of these. Okay, so 4 to the x equals 2 to the 3x minus 12. So here we have an equation. There are no logarithms in it to start with. Okay? So what I want to think about here in solving it is think, okay, look at the bases on each side. One side's a base 4, the other side is a base 2. Are they related? Are 4 and 2 related? 4 is actually what? 2 squared. If they're related like that, that's how I want to solve it, is by using that relationship. Okay? So 4 is really 2 squared. That's a 3x minus 12. Sorry. They're related by the same base. I could rewrite them as having the same base. 2 times that x is 2x, right? So we have 2 to the 2x equals 2 to the 3x minus 12. What does that mean about these two sides? They got to be equal. The exponents have to equal each other. If it's 2 to some power and gives me 2 to some power, those exponents have got to be the same. Okay? So that's what we're going to do. We're going to set those exponents equal to each other because the bases are the same. If the bases are not the same, we can't do that. Okay? Keep that in mind. If the bases are not the same, we can't do that. They have to be able to rewrite them with the same base. So then solve it. Be negative 1x equals negative 12. X is equal to 12. So we get a solution. That's always nice. Because we can take that solution and plug it back into the original, make sure it's correct. And it is. 12 does work for that. Example B. Just go over there to the right there. 9 to the 2x equals 27 to the x minus 1. Those bases are not the same, but are they related? How are they related? 9 times 3 is 27, but 9 is really 3 squared, and 27 is really 3 to the third. So we could rewrite them with a base of 3 because they're related by 3's. So 9 becomes 3 squared. So I'm rewriting that problem. 27 becomes 3 to the third. And then I follow exponent rules. Because I could get the bases the same, I'm going to use the exponent rules to solve this. If I can't get the bases the same, I can't do that. Okay, so on the left side here, 3 to the 2 to the 2x is actually 3 to the 4x, right? You multiply those two. On the other side, we end up with 3 to the what power? 3x minus what? 3. Because we're going to distribute this 3 to both terms. 3 times x is 3x, 3 times 1 is 3. So 3x minus 3. Now that the bases are the same, we got an easy equation to set up and solve. 4x is equal to 3x minus 3. This one's really easy to solve. X is negative 3. And if you plug that into the original problem, it does work. We get a solution out of that. If we can get the bases the same, that can be done. All right. Sample C. 81 to the 3 minus x equals 1/3 to the 5x minus 6. Throwing that fraction in there always gives us a little bit of a, oh crap, I don't know what to do. But let's think about 81 and 1/3. How are they related to one another? Exponentially related to one another. What do we know about 81? It's 9 times 9, it's 9 squared. But 1/3 is not a 9. But 9 is really 3 squared, right? Is that what's 81 as a 3? 3 to the 4th power. Okay, and how could we write 1/3 as a 3? 3 to the negative 1. Very good, sir. 3 to the negative 1. So I'm rewriting these as 3s. 3 to the 4th. 3 minus x. 3 to the negative 1. 5x minus 6. So I've rewritten them as a base of a 3 because they were related. 1/3 and 81 were related. So that's going to be 3 to the 12 minus 3x equals 3 to the negative 5x plus 6. Now that the bases are the same, they go away. And we get a nice little algebra 1 problem. Yes, sir. Did I miss multiply somewhere? That should be 4x. Yes, thank you. I did miss multiply somewhere. Thank you. No, I did. My fault. All right, now get x by itself. So I'm going to add 5x and subtract 12. Just doing that in one step. This is, at this point, it's 7th grade math. You get x is negative 6. Now, some of you may be thinking, I didn't know that 81 was 3 to the 4th right off the bat. How do I go about it? If I don't know much about that number, how can I go about deciding what's happening with that number? The way to think about that, to see if you can do the problem like this with the same base, is to do like a factor tree of the number. So like 81, I could break down. I knew it was 9 times 9, but 9 breaks down even further to 3 and 3 both times. So that's what gives us the 3 to the 4th power. Okay, so that's how you would think about a number. So that's like they threw 64 up there. We know 64 is 8 times 8, but maybe the other side has a base of a 2, and we don't know what 64 would be. We don't know that it's 2 to the 6th power. Caught it. But I don't know if I killed it. Nah. Just a little. All right, so factor trees can help you see those types of relationships. That's going to help you. All right, let's look at it. Maybe another one. Let's do this one. 32 to the x power equals 1 over 16 to the 3x minus 2. This one's a little tricky. That's why I put it in the example, because I think it's a little tricky because of the relationship between 16 and 32. What do we know about the relationship between 16 and 32? 16 times 2 is 32, right? But that's a multiplication relationship. We're looking for what kind? Exponential. Exponential is what we're looking for. Because our variable is in the exponent. So we want to think exponentially what's going on. So what do we know about 32 as a number? Yes, sir. It could, but will 32 turn into a 4 as a base? No. So 4 is not the number we're going for. What number would be the number we're going for? 8 times 4 is 32, but that's still not 4 to a power. So maybe we're struggling with that. So let's use that factor tree idea and see how far will 32 break down. So I'm going to go over here and I'm going to do a factor tree for 32. We know that's 8 and 4. That's 4 and 2. There's 2 and 2. And 4 breaks down to 2 again. 1, 2, 3, 4, 5 2s. What about 16? Yeah, so this would be, 8 and 2, 4 and 2. It's 2 to the 4th. So 1 over 16 would be 2 to the negative 4. So this is how we would break that one down. 2 to the 5th, the x equals 2 to the negative 4 to the 3x minus 2. You can exponentially how that works, how those are related, 32 and 16. All right, that's 2 to the 5x equals 2 to the negative 12x plus 8. Check my math. I won't screw another one up. 5 times x is 5x. I got that side right. This side be negative 12, and that is positive 8. Okay, so I got that right. Okay, and then I just set them equal to each other. Bless you. Add 12x. Be 17x divided by 17. And it's okay we get a fraction answer. That's not unheard of. It's a number. That's what we're going for. If we plug that number back in to the original problem and check both sides, we get they're equal to each other. So it does check in the original problem. So first 4 examples here, we've tried to get the same base on each side because we could. Okay. So always look for that route first because it's easiest. Okay, or I think it's easiest when it's done that way. It keeps you from having to simplify a bunch of logs, is the idea. And we don't want to have to simplify a lot of logs that are unnecessary to solve the problem. So let's look at this problem and recognize the difference. 4 to the x is equal to 11. So that's a very innocent looking problem. It doesn't look very complicated at all. But if we think about it the way we did the first 4 examples here, are 4 and 11 related exponentially? Not at all. There's no way, there's 4 squared is 16. That's not 11. 4 to the first power is 4. That still doesn't get us 11. So they're not related exponentially. So what we want to do is solve that because we can't do it with exponential notation. That's where we say, okay, well, I know it's an exponent on the variable, right? So that means I need to use logs to solve this. Okay, so I'm going to use a log to solve this. And here's the trick. What's the base on this side? That's the log base I want to use. If I do log base 4 of 4 to the x on both sides, I do use a log base 4. That's legal in math because I did the same thing to both sides of the equation. Remember, with solving equations, you have to do it that way. So I did the same thing on both sides. What happens right here? Log base 4 of 4 cancels out. What's left on the left side? X by itself. Yeah, I'm finished. So I got X equals log base 4 of 11. And I can get a decimal approximation for that as well. And I want to. I want you to get the exact answer and a decimal approximation for that. So somebody crank out a decimal approximation. 3 decimal places on that for us. Should be 1 point something, I know, but I don't know what. What we got? 7297. So the 7 makes the 9 go up, which makes the 3 go up. So 730 would be the decimal approximation for that to 3 decimal places. Okay, that's nice and easy. Okay. Look at example F. 7 to the 9x equals 15. This one's a little more obvious. Maybe not more obvious, but still obvious that 7 and 15 are not related, right? Not at all. Not. They probably don't even know each other. Okay, so we can't change the 7 into a different base or the 15 into a different base. They're both odd numbers that don't work out really nicely exponentially, and neither of them work out exponentially. So what can I do to get rid of this base that the x is on? What log could I use? Log base 7. So if I do log base 7, 7 to the 9x is equal to log base 7 of 15. What happens to the base 7 and the log base 7? They cancel each other out. So I've got 9x is equal to log base 7 of 15. I'm not as excited about that one because I'm not done. Right? Because I got 9x is equal to this junk over here. How do I get x by itself? Just simply divide everything by 9. X is equal to log base 7 of 15 divided by 9. And we're going to get a decimal approximation for that. So we're going to do the log base 7 of 15 first, and then divide that answer by 9. Let's see. Math. Log base 7 of 15. How much? Wait, 155. Yeah, the 6 makes the 4 go up. 0.155. Pretty easy, right? Doesn't get much harder, guys, I promise you. Okay, let's look at 9 to the x power plus 6 equals 41. Well, what's different about this one that the other ones didn't have? It's got an extra piece, right? Yeah, it's got some more stuff. That plus 6 in there. How can we get rid of that? Move it over to the other side. Get rid of it. Subtract. 9 to the x equals 35. Are 9 and 35 related? No. Man, that means I got to do what? Use a log, right? Which log do I use? Log base 9. Log base 9 of 9 to the x equals log base 9 of 35. I'm excited about this one because that means I'm done. Because the log base 9 and 9 cancel each other out. And there's log base 9 of 35. And I just need to get a decimal approximation for that. Between 1 and 2, because 9 squared is it's 1 point something. 618. We've simplified. Yeehaw. All right. So far, none of the problems we've had a log in them to begin with. So we've done exponential problems. We used a log to solve the last several. Let's get to some that actually have a log in the original problem, which is where we'll get to use our properties that we've been talking about today. Okay, so let's kind of dip our toe into the water with that. Let's say we had log base 5 of 4x minus 7 equals log base 5 excuse me, of x plus 5. Both of these sides have a log on the side, together. Okay, they have one log on each side. That is the same thing as what we were dealing with when we had the same base on each side. Right? In the first 4 examples we did, it's exponential. These are logarithmic. The math that makes those logs cancel out is called an exponentiation. Fancy words for saying make 5 the base. If I do that to both sides, it'll get rid of the logs. So like those problems on that handout where we had a 10, log base 10 of something, and it canceled each other out. We're doing that to both sides because these are going to cancel the logs. And then we just got an easy algebra, 7th grade math equation to solve. The 5, the exponentiating with the 5, whatever the base of the log is, you exponentiate with that, it gets rid of it. So all the clues are in the problem. So these cancel each other out, leaving us 4x minus 7 equals x plus 5. Well, that's a pretty easy problem to solve. I just add 7 and subtract x. So that's 3x equals 12. Divide by 3. X is 4. We do need to check that in the original. One of the stipulations with logarithms is you cannot take the log of a negative number or 0. So as long as this doesn't get us a negative number up here, we're good. So when we go back to check that, since the original problem had logs in it, that's why that's important. So if I plug a 4 in, that's 16 minus 7. That's a positive number. That's okay. Over here, 4 plus 5 is 9. That's a positive number. That's okay. So I got to check that in the original problem to make sure I don't end up taking the log of a negative. Because if you cannot take the log of a negative number. It doesn't. It's an undefined operation. Okay. Let's look at this problem. Log base 4 of 5x minus 1 equals 3. So a little change up here that it doesn't have a log on both sides. But how could I get rid of that log? How did I get rid of it on the previous problem? I can't just introduce a log on the other side because that'd be double log on the left side. We don't want to do that. What's the base of the log on the left side here? 4. If I exponentiate with the 4, it'll get rid of that log on the left side. But I got to exponentiate on the other side. So it's 4 as the base now here, and 4 as the base here. So this little symbol here, I don't know if I explained that earlier. That's just the caret symbol, meaning this is now an exponent. So over here it's 4 to the 3rd power, which is what? It's a number, right? 4 to the 3rd power is 4 times 4 times 4. That's just a number. Over here, the log cancels out. And I've just got 5x minus 1 equals 4 to the 3rd power. But we know 4 to the 3rd power is really 64, right? 4 times 4 is 16, and then times another 4 would be 40 plus 24, 64. So we get a number there. And now, that's 7th grade math right there. Anytime I can turn work into 7th grade math, I'm pretty good at 7th grade math. Okay, so it's getting it there is the hard part. So I'd add 1 and then divide by 5, right? Plus 1, that's 65. And that's great because 5 does go into 65 13 times. I get x is 13. I want to make sure that doesn't give me a negative in the original problem. 5 times 13, 65 minus 1 is 64. That's definitely not a negative number, so that's okay. So I don't throw that answer out. Okay? Not hard, just different. Not hard, but different. Example J. Log base 7 of 3x minus 2 is equal to 2. Two more examples after this. Did this. Did two more examples. Two more examples after this. What gets rid of the log? 7 as the base. So that ends up being 7 squared over here on the right, which is what? 49. 3x minus 2 equals 49. Solve that. It's like I meant for it to work out nice. 49 plus 2 is 51. Divided by 3, 17. Works out real nice. So still haven't used our properties too much yet. The last two examples do, I promise. Okay, so let's look at those. Example K. That's the worst looking K. It's not much better. I give up. Log 2x plus log x minus 5 equals 2. All right. So this problem looks different because it has two different logs, or two logs on the same side. And we haven't had that. We only have one log in the problem, or a log on each side. And this one has two logs on the same side and then a plain number on the other side. And so that tells me this one's different. Now, on the left side, what's going on between the two logs? They're adding. What property did we talk about earlier that changed addition? It turns it into multiplication. So I could rewrite that as one log that's multiplication on the inside. So this side here can condense to be log of 2x times x minus 5. So I've condensed this thing into one log, and now it's like the problems we were just doing, because I can get rid of one log. Can't get rid of two logs, but I can get rid of one. How do I get rid of this log? Remember it's what base is it? It's base 10. So I'm going to use that as the base. These cancel. I get 2x times x minus 5 is equal to 10 squared, which is 100. And now I got to solve that. Well, Algebra 1 class, we learned about solving problems that had two factors over there. You got to multiply them together. And you get a quadratic because it's got x squared in it. And if you're going to solve a quadratic, what does it have to be equal to? 0. So we're going to move the 100 over. 2x squared minus 10x minus 100 equals 0. And then we know that all of those are divisible by what? 2. So I'm just going to divide them by 2. And then I'm going to factor it. Negative 50 had to be -5. Negative 10 and 5. That's x minus 10, x plus 5. So that means x equals 10 and x equals -5. I get two solutions. I've got to check each one in the original problem to make sure I'm not taking the log of what kind of number? A negative. If I go back to the original, if I plug 10 in, that's 20. Log of 20 is okay. 10 minus 5 is 5. Log of 5 is okay. If I plug in -5, what's 2 times -5? -10. That's the log of a negative. So that means the -5 gets thrown out. It's an extraneous solution. So x equals 10 is the only answer that counts for this one. -5 gets thrown away because it's it doesn't work in the original. Okay. All right. Last example of the year. Take a moment and smile really big because it's the last one of the year. I'm excited. It's a doozy. Log base 4 of x plus 12 plus log base 4 of x equals 3. It's really not that bad. It's just like that. Just different numbers. What does the left side turn into? Well, the addition turns into multiplication, right? So that's log base 4 of x squared plus 12x. I just go ahead and multiply that together. And then how do I get rid of the log? Exponentiate with 4. 4 to the third power is 64. X squared plus 12x equals 64. And get it equal to 0. Try to factor it if possible. If I can't factor that, what's my other option? Quadratic form. That we've done that. All that stuff is still in play. But I think this one factors. It'd be -8, -4. No. It'd be 16 and 4. -4. So x plus 16, x minus 4. So x equals -16 or x equals +4. Which one do we keep? The 4, why? Yeah, because it keeps a positive in the logs in the original. The -16 does not, so it's extraneous. So x equals 4 is the only answer we keep. Oh my goodness, it was the last lesson. And that means this is the last assignments that you have for the year. Oh my gosh, that's exciting. Yeah, tomorrow is a work day for sure. Page 510, 15 through 30, 33 through 41 odd. Let's do all of these because that's some property stuff, and just do the odds on that one. And on page, well, heck, never mind. Let's just do this. What in the world? All right. We made it through the lesson though. Page 510, 15 through 29, and then 33 through 41. Odd on both of those sets. And then section, the last section, page 519. Let's do 3 through 43 odd on those. There's our assignment for tomorrow. You're welcome to start on it tonight if you want, but it's wonderful to be done. All right.